Moisture in the air, from invisible vapor to wild weather. Atmospheric moisture is all about how water moves between the surface and the air, constantly cycling through evaporation, condensation, clouds, and precipitation. Think of the atmosphere as a leaky storage tank, whose capacity depends strongly on temperature. Warm air can hold a lot of water vapor, while cold air can only hold a little. Moisture and humidity. Water gets into the atmosphere mainly through evaporation from water bodies and soil, and transpiration from plants. Together, this is often called evapotranspiration. At any given temperature, there is a maximum amount of water vapor that air can hold before it becomes saturated, and this saturation limit rises quickly as temperature increases. Absolute humidity is the mass of water vapor per unit volume of air, usually expressed in grams per cubic meter, and it changes whenever the air parcel expands or contracts as it moves up or down. Specific humidity is more robust. It is the mass or weight of water vapor per unit mass of air, and it stays the same as long as no water is added or removed, even if the parcel changes volume. Relative humidity is what weather apps usually show. It is the ratio as a percentage between the actual water vapor in the air and the maximum possible at that temperature. Because warm air can hold more water vapor than cold air, 50% relative humidity at 25 degrees Celsius represents much more water than even 100% relative humidity at 5 degrees Celsius. So a mild, humid afternoon can carry far more water than a chilly, saturated morning. Relative humidity naturally falls in the warmer middle of the day and rises again in the evening and overnight, even if the actual water content barely changes. Evaporation and condensation. Water in the atmosphere can be a gas, vapor, liquid, droplets, or solid, ice, and switching between these states involves absorbing or releasing energy known as latent heat. To evaporate 1 gram of liquid water at typical atmospheric temperatures takes roughly 600 calories of energy, which cools the water surface and the air just above it by a few degrees, unless other heat sources make up the difference. Evaporation is strongest when 3 conditions line up. The air is relatively dry, the water surface and the air above it are warm, and there is enough wind to sweep away the moist air and replace it with drier air. Condensation is the opposite change, when vapor turns into liquid or ice once the air reaches saturation, either because more moisture is added, or more commonly, because the air cools to its dew point. In the lower atmosphere, there are plenty of tiny particles such as sea salt, smoke, and dust that act as condensation nuclei, so vapor has surfaces on which to condense. Cooling mechanisms and fog. Air can cool to the point of condensation in several ways. In radiation cooling, which is common on clear, calm nights, the ground loses heat rapidly to space and cools the air in contact with it. If the air is moist, dew, radiation fog, or frost form, depending on whether the temperature is above or below freezing. In advection cooling, warm, moist air moves horizontally over a colder surface, such as a cold sea current or snow-covered land, producing advection fog in many coastal areas, including the famous June gloom along parts of the California coast. Cooling can also be driven by uplift rather than horizontal movement. Orographic uplift happens when moist air is forced up over hills or mountains, while frontal uplift occurs when warm air is pushed up along a front, where it meets a colder, denser air mass. Convective or adiabatic cooling is common on sunny days. Surface air warms, becomes buoyant, rises in thermals, and cools as it expands in the lower pressure aloft, even though it does not lose heat to its surroundings directly. Fog is essentially cloud at ground level and is classified mainly by how the cooling occurs. Radiation fog forms overnight when the ground cools under clear, calm conditions and chills the air just above it. It is especially frequent in autumn and early winter valleys. Advection fog develops when moist air flows over a cooler surface, such as warm air blowing across a cold ocean current, while steam or evaporation fog appears when very cold air moves over much warmer water, and the rapid evaporation plus mixing quickly saturates the shallow air layer above the surface. Adiabatic processes and lapse rates. When air moves up or down in the atmosphere, it experiences pressure changes, which cause temperature changes without direct heat exchange with the environment. These are called adiabatic processes. Rising air expands in the lower pressure aloft and cools, while sinking air is compressed and warms. These vertical motions are key to cloud and precipitation formation. In unsaturated or dry air, temperature typically changes at about 10 degrees Celsius per kilometer of ascent or descent, known as the dry adiabatic lapse rate. Once rising air has reached its dew point and condensation begins, latent heat is released, so the cooling rate slows to the saturated adiabatic lapse rate, usually between about 4 and 9 degrees Celsius per kilometer, depending on how warm and moist the air is. These adiabatic lapse rates apply specifically to moving air parcels and should be distinguished from the environmental lapse rate, which is the actual observed change of temperature with height in the surrounding atmosphere. Clouds, stability, and thunderstorms. Clouds are visible evidence of condensation and come in many forms, but a simple distinction is between stratiform, layered, and cumuliform, heaped or vertically developed. Unstable conditions with strong convection tend to produce towering cumuliform clouds, while stable or gently mixed air favors more extensive layers of stratiform cloud. Atmospheric stability describes how air parcels behave when they are lifted. If the environmental lapse rate is greater than the dry adiabatic lapse rate, rising parcels stay warmer and lighter than their surroundings, so the air is unstable, and vigorous vertical cloud growth, including cumulonimbus and thunderstorms, is likely. If the environmental lapse rate is smaller than both the dry and saturated adiabatic rates, the air is stable. Lifted parcels quickly become cooler and denser than their environment and tend to sink back down. Conditional instability exists when the environmental lapse rate lies between the two adiabatic rates. Unsaturated parcels are initially stable, but once they reach saturation and follow the saturated rate, they can become warmer than their surroundings and accelerate upward, often leading to deep clouds and storms. Thunderstorms are intense weather systems that form when instability extends through a deep layer of the atmosphere, enabling strong updrafts inside cumulonimbus clouds. Rising air releases latent heat as condensation occurs, further strengthening the updrafts and allowing clouds to grow to the tropopause, where their tops often spread out into the classic anvil shape, around 10 to 16 kilometers, depending on latitude. Eventually, downdrafts loaded with rain and hail become dominant, bringing heavy showers, gusty winds, lightning, and thunder as the storm matures and then decays. Lightning discharges occur because charges separate within the storm, with positive and negative regions forming in different parts of the cloud and sometimes between the cloud and the ground. Collisions between ice crystals and graupel or hail in strong updrafts and downdrafts contribute to this charge separation, creating powerful electric fields that accelerate electrons and can generate high-energy emissions such as gamma rays. The rapid heating of air along the lightning channel causes explosive expansion and vibration of the air, which is heard as thunder. Precipitation and hail. The growth of cloud droplets into raindrops is not just a matter of simple condensation. It usually requires special microphysical processes. In mixed-phase clouds, at temperatures roughly between -5 degrees Celsius and -25 degrees Celsius, both supercooled water droplets and ice crystals can coexist, setting the stage for the Wegener-Bergenfeinsen process. Because the saturation vapor pressure is lower over ice than liquid water at the same temperature, vapor tends to deposit onto ice crystals, while nearby supercooled droplets evaporate. The ice crystals grow, often aggregating into snowflakes that may melt into raindrops as they fall into warmer layers below. Cloud seeding experiments and detailed field studies over the last decade have used this understanding to test how efficiently ice crystals can grow at the expense of cloud droplets, improving knowledge of precipitation formation and model performance. In very warm tropical clouds that do not extend into the mixed-phase temperature range, precipitation often forms by collision coalescence. Larger droplets grow by colliding with and absorbing smaller ones, helped by strong updrafts and sometimes electrical interactions within the cloud. Hail forms in particularly strong cumulonimbus clouds, where vigorous updrafts repeatedly carry ice pellets up and down through regions of varying temperature and liquid water content. Each cycle can add a new layer of ice, sometimes creating the characteristic concentric structure seen when a hailstone is cut open, until the stone becomes too heavy for the updrafts and falls to the ground. Fronts, depressions, and occlusions. Fronts are broad transition zones between air masses with different temperature and moisture characteristics, often sloping gently upward from the surface into the upper troposphere. A warm front marks the advance of warmer air replacing cooler air, while a cold front marks colder air undercutting and lifting out warmer air. Both are associated with clouds and precipitation, but their cloud patterns and timing differ. Active fronts with strong uplift in the warm air are sometimes called anafronts, while fronts where the warm air is largely sinking and weather is weaker are known as kata fronts. In the mid-latitudes, most fronts are embedded in low-pressure systems known as extratropical cyclones or frontal depressions, which typically last from several days to about a week. These systems often originate as waves along the polar front jet, then deepen and wrap warm and cold fronts around a central low. Over time, the faster-moving cold front can catch up with the warm front, creating an occluded front where the warm sector is lifted off the ground and the system gradually weakens. Such cyclones often come in families along the polar front jet, leading to prolonged spells of changeable, unsettled weather across regions like the North Atlantic and Northwest Europe. Local winds and small-scale climates. On clear, calm days in hilly or mountainous areas, slopes heat up in the sun, and the air next to them warms and rises, drawing air upslope as an anabatic or upslope wind. After sunset, the slopes cool quickly, the air in contact with them becomes colder and denser, and it drains downslope as a katabatic wind, often pooling cold air in valley bottoms and creating frost hollows. The strength of these flows depends on slope angle, surface cover, such as snow or vegetation, and overall weather conditions. Coastal areas experience similar small-scale circulations known as land and sea breezes.
During the day, land warms faster than nearby water, lowering surface pressure slightly over land and drawing in cooler, often more humid marine air as a sea breeze with a compensating return flow aloft. At night, the pattern usually reverses as the land cools more quickly than the sea, producing a weaker land breeze. Urban climates and urban heat islands. Cities significantly modify local climate through their buildings, surfaces, and emissions. High-rise structures can channel and accelerate winds along streets, a kind of Ventura's effect, increasing turbulence at street level, especially in winter storms. Urban areas also tend to have lower relative humidity near the surface due to reduced vegetation and altered soil moisture, while the abundance of rough surfaces and heat sources can enhance convection and make thunderstorms slightly more frequent or intense just downwind of large metropolitan areas compared with nearby rural regions. The urban heat island effect is one of the most studied aspects of city climate. Concrete, asphalt, and brick store heat during the day and release it slowly at night, while anthropogenic heat from buildings, traffic, and industry, together with reduced sky view and air pollution, keeps urban air warmer than surrounding countryside by 1 to 3 degrees Celsius on clear, calm nights, and sometimes more in very large cities. When plotted on an isotherm map, temperatures usually show a bullseye pattern, with the highest values in dense city centers and a gradual decrease toward the suburbs and rural fringe. Thank you for listening to this Geography Expert podcast. You can find access to all my free resources through my website, www.richiecunningham.com, including links to my Geography Expert Substack and podcasts.